So here's problem number 51. We're not going to do the entire problem. We'll only do the setup part, and then we'll assume that we can handle the integration later. Let's take a look at what these graphs look like. And again, I have an expectation that these particular two polar graphs that you've memorized what they look like. The sine one. The sine one.
Yeah.
You want to call it the vertical circle? Sure. The cosine one. The horizontal circle. Both of these are coming out to 2. They both have radius 1. And so what we're interested in is
Shared area.
the shared area. The area that's in between, that's in here. Now, I've got a crazy thought. Seeing that we know that the area formula for polars is 1/2 r squared d theta. And again, because the harder part is, what is the values of theta that range over this? I'm going to go and make one proposal. First of all, I don't need to find the shared area. I think there is symmetry. I only need to find half the shared area. All right?
Yes.
So let's focus on, let's say, the cosine curve. Or the sine curve. No, the sine curve. Sine curve's in black, right?
Yeah.
So I'm going to say, can we just find that area there and we'll double it? So I'm going to say the area is something doubled, and the thing that I'm doubling is the sine curve.
Squared? Or no?
Oh yeah, quantity squared.
And what are the limits?
What are the limits of integration?
Zero.
I think one of them is obvious.
Zero.
Okay? Because this sine curve it starts here and it goes this way. So it starts with theta equals 0. Great. I agree.
Yeah. I have no idea. How to make one circle, what would the upper limit be?
To make one circle, it goes from 0 to pi.
Pi, right? So wouldn't that be pi over 4 because it's a quarter of a circle?
It is pi over 4. That line of symmetry is right at that 45-degree angle.
Yay!
Indeed. And that's it.
All right. Next problem.
Well, you know what?
Might as well do it.
Those 2's cancel. So we get a 2, and we get a sine, sorry, pi over 4. We get a sine squared d theta.
Wait.
It shouldn't be
If
4
we-
on the outside?
if we-
Pulled out.
4 on the outside.
Pull a 4 out. That's what I wrote. I wrote a 4 there.
I see.
Yeah.
Very fancy four.
Very fancy 4. Answer. I'm not going to solve that, but what would you use to solve it? The power reducing identity.
Yay! That 1/2.
1/2 minus 1/2 cosine 2 theta. All right, so that's number 51. Let's take a look at setting up problem number 53.
Just replace the signs.
Problem number 53, shared by the circle r equals 2,
Circle with radius 2.
circle with radius 2, and then the cardioid r is equal to 2 times 1 minus cosine. Is that the one with the butt?
The tushy.
Austin, you were saying something.
No, the ball
Danny
is
said it
like
first.
-1 plus sine theta, I
Someone's stupider over there.
Okay, 2 times 1 minus cosine 2 theta? Is that right? Is it 2 theta?
Yeah. No, theta.
Just plain old theta? Well, there's a way to find out.
Yeah.
Winner, winner. There's
Chicken
one
dinner.
ending parenthesis,
All right,
not two.
so zoom 0. Okay, let's take a look at that while it's graphing.
What?
Oh,
How come yours doesn't take as long?
Okay, that's
What's
even
it-
worse.
do you remember why it's doing that? You remember how at the last problem, what did we do? We changed the values that theta takes on, how about we try going from 0 to 2 pi? Zoom 0. I feel like I should be like telling jokes while we're waiting for the calculator to do this work.
Feel
We're all
free if
kids.
you know any.
What's worse than the processor on the calculator?
I don't know, what is worse than a processor on the calculator?
Two processors on the calculator.
No.
What's the answer, Allison?
That would be better because
I said Windows.
Oh,
What did you say?
As for math.
Totally should have said Linux.
Okay.
what's better than Windows?
The movie.
I didn't even say Linux.
Nothing. That's how I respond to that, man.
Okay.
Why? That's-
So this is the cardioid. This isn't the butt version of it.
It's the
Okay.
That's number line.
Okay. So what's going on in terms of the area shared by these two?
it's the picture that comes out of the copying machine when Bart Simpson goes on.
Okay. Well, this is not. This is the aspect ratio here is off. So this is 2. There's a circle with radius 2.
And there's two
Yeah.
other half circles.
And then we have,
That's
so we have these. These are, by the way, those are not circles. They're not half circles either. Not, okay. Okay, so here's what we've got. I know what half of the answer is already.
Yeah.
Because I know the area of this circle already. This is a circle with this is half of a circle with radius 2. Circle with radius 2 has area 4 pi. So this part is 2 pi. Now, what's left? I need to find the integral expression that's going to be able to handle this. Now, do we know handle all of this? Do we know the range of thetas that will give us that little bump on the cardioid?
We can figure it out.
we could try.
I'm going to guess that it's going to be negative pi over 2 to pi over 2.
Wow.
Yeah,
Good
sounds
guess.
about right.
I would have to.
All right.
agree.
So let me test my theory.
Oh, I can see.
Window, negative pi over 2 to pi over 2, and graph it.
That looks to me like it's working.
Looks to me like I've nailed it. All right. So if that's the case, we can go ahead and write our expressions.
How do you know it's negative 5 over 2 to 5 over 2?
Well, first of all, when I'm looking at this polar curve, there's no multiplier inside the cosine. So when I think of cosines and where they reach these important points,
He's looking for cosine theta equals 0.
right?
Oh,
So think about where cosine theta is equal to 0. Where's cosine theta equal to negative 1 and 1? All right. So what do we end up having? The two parts of the area can then be described as
2 pi plus.
2 pi plus the integral from negative pi over 2 to pi over 2 of 1/2
2
times 2
1 minus
1 minus cosine theta closes off. All of this is r, so square all of it,
d theta.
d theta.
And then you can do the whole
And then again, because of symmetry, because essentially that cardioid looks like this, right?
Yeah.
Because those two cheeks are the same area, then we could do the double and only go from 0 to pi over 2 trick. All right, so there's 53. We're gonna do one more.
55.
All right,
There we are.
inside the circle, pi over 2, and outside the cardioid. This is the same. This is
Just shift it over.
well, we have this circle. Okay, and what I think we saw, when it's cosine, it's this way. When it's sine, it's this way.
Yeah. Should be. So then
I don't know. Do you want to test that? I think that's the shape of that cardioid.
negative pi. Or no,
No, I think I got it backwards.
Yeah.
I can tell you right now.
I think it's up.
I think it's up.
It is.
So this is the real cardioid, right? The one that actually does look like a heart. And I want my window from 0 to 2 pi to see the entire thing. And zoom fit.
Was it when cosine's positive and when sine's positive, it faces that way?
Well, I was just thinking, the reason why I think it's the one where the humps are on the top is because in the cosine version, the humps were in
Yeah.
the humps were where x
It's
x and y were both positive. So I think what happens is that when you do the sine version, it goes that way. So just in time for Valentine's Day, I give you this. I give you this cardioid.
Thank you. You guys write poems about Valentine's Day last year?
No, you had to write poems.
That was
about
for
it.
extra credit.
Okay, so there's our cardioid shape. So my drawing is off. My drawing is off. So no green curve. Almost wish I had a do-over. So the cardioid's going like this. Okay, and we want outside the circle but inside the cardioid.
The mouth would help.
So it's elegant.
No, outside the cardioid, inside the circle.
So outside,
Yeah.
inside the circle, outside. So we want this area here.
Yeah.
This area here. Is that right?
That's correct.
Okay.
4 pi minus what we got left.
Well, half of a circle is 2 pi, right? Minus,
Zero to five. Yeah, 0 to 5. That's our sign. Zero.
don't forget the square. So I think there's your area. All right? Again, the tricky part, trying to find out where those limits of integration happen to be. All right, so let's close off that.